This is the practice assessment for sections 3.1 to 3.4. The first thing that we talked about was determining symmetries, and we talked about determining if an equation was symmetric over the origin, the x-axis, the y-axis, the line y equals x, and the line y equals negative x. So I like to do this in a nice organized fashion. When you check symmetry over the origin, you replace x and y with negative x and negative y. So I'm going to replace x and y with negative x and negative y. The question is, do I get the same equation that I began with? Well, what happens when you multiply two negatives together? You get a positive, and that's the same equation I started with. So this graph is symmetric over the origin. To check symmetry over the x-axis, you replace just y with negative y. Well, when I do that, I get x times negative y equals 5. A positive times a negative is a negative. This is not the same equation I started with, so it's not symmetric over the x-axis. To check symmetry over the y-axis, you replace x with negative x. Let's change that. But you don't do anything to y. So I've got negative x times positive y equals 5, which is negative xy, which is not the same equation. How about when I check symmetry over the line y equals x? That's the one where you flip x and y. There are circumstances under which when you flip them, you will get the same equation. This actually is the same equation as the first one, because this says y times x, and the original problem was x times y. Well, isn't 3 times 2 the same as 2 times 3? That's because multiplication is commutative. So it is symmetric over the line y equals x. To check symmetry over the line y equals negative x, not only do you flip them, but you make them both negative. So when I flip them and make them negative, not only do I get a positive when I multiply them, but because multiplication is commutative, it is symmetric over the line y equals negative x. So it turns out that x times y equals 5 was symmetric over the y-axis. It was symmetric over the origin, and it was symmetric over the line y equals x and the line y equals negative x. Now the math does get more complicated when you try y equals negative 2 over x squared. In order to make this problem a little more manageable, when you have a fraction that's negative, just make the numerator negative. It'll make your life a lot easier. So when I check symmetry over the origin, if I replace x and y with negative x and negative y, will I get the same equation I started with? Well, the denominator becomes positive x squared, and then these two negatives both cancel each other. That is not the same equation I started with. When I check symmetry over the x-axis, so y becomes negative, but nothing happens to x. That's the same thing I had happen here. Those two negatives cancel each other, and now it's positive 2 over x squared, which is not the same equation I started with. Now I'm going to try symmetry over the y-axis. So I'm not going to do anything to y, but I'm going to make x negative. Well, when I square a negative, I get a positive, and that is the same equation I started with. Now let's check over y equals x. If I flip x and y, is it the same equation? Anytime one of the variables has an exponent that's different from another variable, it's not going to be the same equation. Because in our original equation, we want x to be negative. And a lot of times what happens is if y equals x doesn't work, y equals negative x probably also doesn't work, because in this case, y is still squared, but I want x to be squared. So even if I simplify it, it's still not the same equation I started with. So it turns out that this equation is only symmetric over the y-axis. Now let's do x equals y squared plus 3. Now if you can plug them into your calculator and see the symmetries, that's great. But not everything is designed to plug in our calculator. And if you can't use Desmos on the test, then you have to be able to do this on the calculator. So let's check over the origin. If I make x and y negative, do I get the same equation I started with? Well, the negative y becomes positive because it squares, but nothing happens to the negative x. And really, this is the new equation, which is not the same equation I started with. X-axis, nothing happens to x, but y changes, but I'm squaring a negative. And it turns out it is the same equation, so it's symmetric over the x-axis. The y-axis. You make x negative, you don't do anything to y. Well, that's not the same equation I started with. Anytime your variables have different exponents, when you check symmetry over y equals x, when you switch your x and y, it's not going to be the same equation because the original problem, y was squared. We want y to be squared. It's not, so it's not symmetric. And a lot of times, if it's not symmetric over y equals x, it's probably not symmetric over y equals negative x either. Describing how two graphs are related is asking for the transformations that's been performed on the parent function. In this case, y equals x squared is the parent function. So the things that have changed in g of x is it has been reflected over the x-axis. That's what a negative in front of the original function does. And whenever you add a number in a set of parentheses, it shifts it to the left, and it went to the left 3 units. At the beginning of the problem, make sure you ask yourself how many transformations are being performed on the parent function before you write them down. In number 5, the parent function is absolute value of x. In the new function, there are 2 transformations. Whenever the number you're multiplying the original function by is greater than 1, we say that it stretches vertically, and then it stretches vertically by a factor of 4. And then inside the bars, it says minus 2. That means we're going to move it to the right 2. Now remember, another way of doing this is if you forget what the transformations are, graph the parent function and graph the new function and see if you can see what changes occurred. In number 6, the parent function is x cubed. In the new function, whenever the negative is in the parentheses and not outside the parentheses, instead of reflecting over the x-axis, we say that it reflects over the y-axis. And then this is going to move the graph up 5. Anytime you add or subtract a number at the end of the original function, that moves the graph up and down. In number 7, the parent function is y equals the square root of x. In the new function, I'm going to actually rewrite it a little because x over 3 is the same thing as 1/3 x. So I'm multiplying the input by a number inside the radical, not outside the radical. When it's inside the radical, we say that it either stretches or compresses horizontally. When a is between 0 and 1, we say that it stretches horizontally by a factor of 1/3. And nothing else is happening to the original parent function. When you have anything that you need to graph, you have no excuse to not graph it correctly. Graph it in the calculator and use the table functions to find ordered pairs that lie on the graph. Just make sure that the graph you draw looks like the one on the calculator. So number 8, y is greater than the absolute value of x minus 4. Since it's an absolute value function, you know it better look like a v, and if your graph doesn't look like a v, you probably didn't plot enough points. Well, I also know that this is the absolute value function that's been shifted 4 units to the right. So I actually know that I'm just going to shift the vertex 4 to the right and make my v shape. Since the inequality symbol is greater than, it's going to be a dashed v. There are only 2 regions of the graph that could get shaded. You're either going to shade inside the v or outside the v. If you're not sure where to shade, you can always test a point like 0, 0. Is 0 greater than the absolute value of 0 minus 4? You have to do 0 minus 4 first, and then you take its absolute value. Is 0 greater than 4? No. So that means everything outside the v is false, and everything inside the v is probably true. Number 9 is a transformation on the parent graph x squared that's been moved up 3 and stretched vertically by a factor of 2. However, you can just plug this into your calculator to see that the vertex is at 0, 3. And then it goes through 1, 5 and negative 1, 5. And then it goes through, 2, 11 and negative 2, 11. Since the inequality symbol is less than or equal to, the parabola should be solid and not dashed. And there are only 2 regions in which you could shade. You either shade inside the parabola or outside the parabola. If you're not sure where to shade, test an ordered pair like 0, 0. Is 0 less than or equal to 2 times 0 squared plus 3? 2 times 0 squared is 0, so you're left with 3 on the right-hand side. Is 0 less than or equal to 3? Yeah. And that means everything on the outside of the parabola should be shaded. When solving an absolute value inequality, make sure that the absolute value is isolated before you set up your 2 inequalities. Since there's a 3 in front and it's being multiplied, we're going to get rid of it first by dividing. Now we're ready to set up our 2 inequalities. They are x minus 5 is less than 3. The other one is x minus 5 is greater than negative 3. I'll determine in a minute whether it should say and or between them. So the first answer is x is less than 8. The second answer is x is greater than 2. If I draw myself kind of a quick sketch on the number line, I'm going to be able to figure out really quickly if it's and or. So if I call this 0, and this is 2, 3, 4, 5, 6, 7, 8, I should have an open circle on 8 with an arrow pointing to the left. And I should have an open circle on 2 with an arrow pointing to the right. They overlap. It's and. The last thing we reviewed was finding equations of inverses, which is something we did in Algebra 2. In order to find a general equation of an inverse, you're going to switch x and y and solve that new equation for y. So I'm going to add 4 and then divide by 5. And that's the equation of my inverse. And the inverse is denoted with what looks like f to the negative first power, but really isn't. The second part said state whether it is a function. You have 2 options for doing that. You can either graph the original function, 1, 2, 3, 4, here's the original function, y equals 5x minus 4, and perform the horizontal line test on it. If you put a horizontal line anywhere on this graph, as long as you never hit the graph more than once, its inverse is a function. Or the other thing that you can do is you can graph the new function, which I'm sure is going to look something like, let's see, if that's the original function, then the new function, I'll use a different color, must look something like this. That's a bad drawing. And perform the vertical line test on the new function, and as long as the vertical line never touches the new graph more than once, it must be a function. And it turns out that the inverse of the original function is a function. Let's do this one more time. I'm going to switch x and y, and this one's a little bit trickier because you got to get that y out of the denominator. What you may not recognize is that this is really a proportion. And how do we solve proportions? Well, we cross multiply. And I want you to notice that when I cross multiply, I did not distribute the x into the y minus 2. The reason is because now I'm going to divide by x. Let's see, I don't even need that parentheses. So I get y minus 2 is equal to 3 over x. And then I'm going to add 2. And that's my new function, or my inverse. And the question is the inverse a function? Well, again, you can go and look at the original graph. The original graph is a rational function that's been shifted 2 to the right, and it's been stretched vertically, so it probably looks, let's see, something like this. That is a function. Its inverse, I'll do that in red, is going to look something like this. And the red graph, which is the graph of the inverse, if you perform the vertical line test on it, you're going to find out that it is a function. The kinds of things you're looking for, whose inverses are not function, quadratic equations, their inverses are not functions. One other thing that I want to mention, be careful when you're dealing with real-world equations, you know, like the area of a circle or the conversion from Celsius and from Fahrenheit to Celsius. When you're finding equations of inverses of actual equations that you would use, we don't switch the input and output. To find the inverse, you just solve for the input. For the area of a circle, the input is the radius. So you would divide by 2, and then you would square root, and this would be the equation of the inverse. Remember, I mentioned in class, the reason I don't put the plus or minus symbol in front of this particular radical is because radius cannot be negative. In the second equation, to find the inverse, you would solve for f. So you would have to first multiply by the reciprocal of 9/5, and then you would have to add 32. And then this would be the equation of the inverse. So the only time you don't switch the input and output is when you're working with an actual equation. When you're working with just general random graphs in x and y, you do switch them. And that's the practice assessment for sections 3.1 to 3.4.